The first section in chapter 4 is about right triangle trig. So now you're going to start working with triangles that revolve around the SOHCAHTOA idea, which a lot of you might be familiar with. And the other thing that we'll study in chapter 4 is working with oblique triangles. Oblique triangles are triangles with no right angles. So when we think about right triangle trig, it's basically taken the idea that you've done from chapter 2 when we said that sine theta was y over r, and if we draw a right triangle like we did with the unit circle to represent those, notice that y represents the side opposite theta and r represents the hypotenuse of the triangle. So when we talk about the cosine of theta being x over r, x is the adjacent side to theta and r is the hypotenuse. So then we have these relationships that change from x, y, and r to adjacent, opposite, and hypotenuse. And the SOHCAHTOA comes from the first letter of each one of these. So sine, opposite, hypotenuse, SOH, tangent, opposite over adjacent, TOA. And so that's where that comes from. And I posted a fun story about the finding of SOHCAHTOA in Doc Sharing. So if you want to smile, it's actually a pretty good laugh at the end. You can look at it. When we look at solving right triangles, we have it in two different ways. We have it where we represent each angle with a capital letter and its corresponding side in small letters. Or each angle is represented by a Greek letter, A for alpha, C is gamma, and B is beta. And then again, their corresponding sides are small letters. So you'll see triangles written in both ways. When we solve right triangle trig, it's just really all about setting it up. Here in this case, if you want to know what the hypotenuse is, and you know that you have a length of 4, and even if they give you that one angle is 57 degrees, the sum of the angles is 180, and one of them is knocked out with a 90 degree. So these two should always sum to 90 degrees. So if I want to know what C is, I have a couple options. We could use cosine because this is adjacent to 57, or in this instance I use sine because sine has opposite over hypotenuse. And so then basically all you have is this linear equation. To get C by itself, you would end up dividing both sides by the sine of 33 degrees. And biggest thing here, watch your mode on your calculator between degrees and radians. And then you get the answer. And then we can use Pythagorean theorem to find the missing side. I know this side is 4. I'm looking for side A, and you found the hypotenuse. The other way you can do it is same technique. You're looking for A. You found that the hypotenuse was 7.34. So you could say that the sine of 57 opposite over hypotenuse, multiply both sides by 7.34 to get A by itself. And then here's another example where you're given that alpha is 11.54 degrees and you get the length of the hypotenuse and the length of one side. So in this case, if you want to know B, well, you would know opposite over adjacent, which is tangent. And so then you can do the work there to get what the side B is, approximately 4.90, or you can also use Pythagorean theorem because you have two sides and you want to know the third side. To get beta, again, it's a right triangle, so you're going to subtract this from 80 degrees, or if you want to verify it, then you would also have the option of saying that the sine of alpha is opposite over hypotenuse. I'm sorry, the sine of this alpha is opposite over hypotenuse. So that's one way to get that alpha is 11.54. We do have cofunction ideas. So this document's available to you in doc sharing, so you can print it off. But just the fact that if you think about it, the sine of theta is equal to the cosine of 90 degrees minus theta. So think of the sine of 30 and how it's equal to the cosine of 60. So tangent and cotangent are considered cofunctions. So the tangent of 30 is equal to the cotangent of 60, and secant and cosecant are considered cofunctions. And then you're going to have a lot of application problems with right triangles because you can find heights, you can find lots of different angles of elevation or angles of depression. So if you go back to the beginning piece of paper here where it says that you're headed toward a plateau 24 meters high and the angle of elevation to the top is 15 degrees, how far are you from the base of the plateau? So angle of elevation and depression both are with the horizon. So your angle of elevation is looking up, angle of depression is looking down. So again, angle of depression is with the horizon. So your angle of depression would be in here if you had one, because it's always with the horizon. But in this case, I know my angle of elevation is 15 degrees. I know that the height of the plateau is 24 meters. I want to know how far away I am. So when you look at the relationship between the angle that you're given, what you know and what you want to know, you have angle, opposite, and adjacent. So we do the tangent of theta is opposite over adjacent, and we multiply both sides by x, which in turn divides both sides by tangent of 15 degrees, and you get that you are approximately 90 meters away from the plateau. And here's an example of what I'm talking about. Angle of elevation is, again, with the horizon looking up. Angle of depression is with the horizon looking down. So watch your angle of depression problems, because a lot of students make the mistake of this angle being in their problem, and that's not what you want. But together they make a 90-degree angle, so the difference would be the angle that you're probably working with in the triangle.